And they could predict up to 5 poses per model. And they had to return this in SDF format, which is a format that allowed us to make sure that connectivity is preserved. We thought this would not be possible with PDB files. And I'll show in a minute why this we think this is important. And so, thank you. And so then, after the experiments, we were joined by Pat for the assessment, and we started thinking, how can we evaluate these predictions? So I have to say, we were very surprised with the reception. 37 groups participated in the ligand assessment, and more than 24,000 ligands were returned by all the participants. That's a huge number. I think we're really happy that that it really worked. And so we then had to figure out how we're going to score that. We, of course, want a score that compares the prediction with the reference target. And we want a set of diverse scores that represent different aspects of the prediction accuracy. There are no well-established scores for these kind of challenges. We really are in a completely new field here. And so we, with the input of Pat, we designed 2 scores, which I'm going to describe in a few slides. The first is a symmetry-corrected pose RMSD. This is similar to what the D3R has been doing, where they used a symmetry-corrected pose RMSD as well. There's just one more thing, because we asked participants to predict the protein structure. The model is not in the same reference frame as the reference. So the first thing we need to do is to identify the binding site in the reference structure. And then we identify the binding site in the model as the same residues. And we can do a superposition of these binding sites. And then we can start to have a superposed model and reference ligand, which we assess with RMSD. I'm not going to go into the details. You all know what RMSD is. What I want to show is the symmetry correction part, because of course, some of these ligands have rotation, they can rotate. And basically, if you look at these 3 oxygen atoms here, they're chemically equivalent, they are the same. You can predict them in any rotation, that doesn't matter. And so we have to take this into account when we score. And the solution comes from the field of graph theory, where there's this a concept of graph isomorphisms, where you can enumerate all the graphs that are actually the identical graphs. And that basically gives us all the possible rotations. But this absolutely requires connectivity. If we don't have the connectivity of the predictions, there's nothing we can do. And so that's also why we have to request a special format. The second score we designed is actually completely new and looks at protein ligand interactions. It's basically a variation of the LDDT score. You all know the LDDT score, which looks at contact conservation, starting from the targets. Here we only look at contact between the binding sites, residues, and the ligands. So that's a rather small number of contacts. There's a few parameters. I'm not going to go into details. A few caveats. There's no penalty for added contact. So if you were to predict an extra residue here, that's not taken into account and not penalized. And also the sequences must match. We had a few issues with some targets where the target had different sequences that the ligands. And so here again, we do a symmetry correction for the same reason as the RMSD. We need to take into account rotations. There's a few more complexities in this evaluation. The first is chain mapping. You've heard about it. Luckily, I was sitting very close to Gabriel Studer, who helped a lot on that. It turns out that ligands and all these ligand scores are fairly local, and the number of chain that's involved is always rather small. So we could always enumerate the full set of possible chain mappings and calculate the scores on all of them and pick the best. So we were quite lucky with that. The next thing that we need to care about is ligand assignment. if, and some of the targets had multiple copies of some of the ligands, and of course there's multiple copies of the ligand in the prediction, how do we know which copy is corresponding to what? So which prediction corresponds to which target ligand? And so what we did was simply to build this table with all the ligands in the reference target in the model. And this is for LDDT-PLI, where we start with the highest score, and we basically assign each ligand in the target and in the model only one to a corresponding ligand. And we work going down into this table to get the final ligand assignment that you can see in the tables on the CASP website. I want to give you a little feel of what these scores do. On the x-axis is the LDDT-PLI. It's a score between 0 and 1. On the y-axis is the pose RMSD. That's a score between 0 and infinity. They're very correlated, but as you can see, there are a few outliers. And what you can also see is that the LDDT, of course, because it looks at a set of threshold distances, as soon as the ligand is too far away, it goes down to 0 actually quite quickly, whereas the RMSD keeps going up for pretty much ever. And so what does it look like? So you want to be basically down here with an LDDT-PLI close to 1 or even of 1. And an RMSD really close to 0, and we were really happy. There are actually quite a lot of predictions in this zone. You cannot see the model ligand because it's literally spot on, and the binding site is also beautifully modeled. So good job here. On the other hand, there are these predictions up here where the ligand is just really far away. So we got quite a few of these. So there are a few outliers where the scores basically give you some different information. Down here, the ligand is placed, and it's a small ion, it's placed perfectly. But as you can see, the side chain in the binding site is rotated, and this is reflected in the LDDT-PLI, which goes down. And on the other side, we have the exact other effect where the binding site is modeled beautifully, but the ligand is actually placed wrong. And because of some artifacts in LDDT, it looks at distances, not at actual orientations. And so you can still get a very good LDDT-PLI for this prediction here. That's why we have the RMSD as well, which will show us that this was not a perfect prediction. And we also have this group of predictions here where we have completely disconnected, again, ligands which were placed really far apart. So yeah, I guess I'm going to leave the stage to Pat for the next.
All right, thanks. So as Xavier was mentioning, this is sort of a new unprecedented area. So from 2015 to 2019, I worked with Romy Amaro and Mike Gilson on the D3R challenge, but compared to what we're doing here at CASP, D3R was child's play, because in D3R, we were giving people a protein structure. So we were giving them a PDB file for the protein, and we were asking them to dock ligands. And then subsequently, we were then assessing the binding pose RMSD and also asking people to predict binding affinities. So, you know, in CASP, we don't have protein coordinates. The binding site is not known. In D3R, we are mainly dealing with drug-like ligands. In this case, as I'll show you, we're dealing with everything from ions up to, I think, our largest ligand has 83 heavy atoms. So relatively large. And then in D3R, we were always dealing with cases where we had a single ligand. In this case, we've got, you know, at max 56 ligands. I think there are only 7 cases that have a single ligand. So it does complicate things. I think we did what we think is the best, but we're hoping to get some input from the community on how this can be done better. We had a mixture of targets. So we had, you know, multimeric targets. We actually started out with 2 RNA targets, but after consulting with the RNA evaluators, they determined that the ligand in one of the structures was not supported by experimental data, so we dropped that one. This was not without its challenges. So this is the first time CASP has done a ligand challenge. It was a brand new format, and not everyone completely grokked that format. So we got submissions that didn't have protein structures. It's kind of difficult to figure out the pose if we don't have the protein structure there. All of these ligands had names so that we could figure out which ligand people were positioning. There were a lot of people who just called them all lig. So we ended up getting very creative in doing things like hydrogen suppressed molecular formulas to try to figure out which ligand people were actually posing. People had ligands as PDB files, which we could sort of sort out. People had proteins as V3000 mol files, which throws out all the residue information. So that made things a little more complicated. I realized that people come from a protein world where bond orders are implicit. That is not the case with small molecules, but we had lots of structures submitted with no bond orders, all sorts of charge states. In one of the challenges, I counted 42 different representations for ATP. So, yeah, there were a lot of nights and weekends spent just cleaning this data up. But I think we know what we need to do now. Next time it'll be much easier. Another thing that was really challenging, and I'll get to this in a minute, is not everybody decided to submit poses for all the ligands. Some people just apparently wanted to just do the ions or just do the organics. So again, it made assessment a bit of a challenge. So, you know, it turned out that despite all of our efforts, about 10% of the submissions we just couldn't process because they didn't contain a protein, or, you know, there was something that we just couldn't fix. And then there were a lot of submissions that just didn't have all the ligands, but still, you know, I feel pretty good. 80% of the submissions we were able to process. This is our first time doing this. So I think this is pretty successful. This is the other thing in dealing with a world where the experimental data comes in after people have made their predictions. Sometimes the number of ligands that the experimentalist originally told us were in there turned out to not be correct. So there were two cases where one case they said there were 4 NAG, turned out the crystal structure had 2. There was one where they said there was 2, it turned out to be 1. And then there were a couple of cases where there wasn't density in the structure to support part of the ligand. So the ligand in the crystal structure or the cryo-EM structure ended up being a subset of what people had predicted. But we worked around that. So here's what we're looking at in terms of the number of heavy atoms. So you can see we've got a lot. So number of heavy atoms on the x-axis, just the counts on the y-axis. So you can see there are quite a few just ions in there, magnesiums, all the way up to this beast over here on the right. So really a wide range of ligands were evaluated. And then this is looking at the number of ligands in the structures. So again, number of ligands on the x-axis, counts on the y. So only 7 structures with just 1 ligand in them, all the way up to this structure H1114 that has 56 ligands in it. And I think I can use that as a way to take a look at some of the challenges that we deal with. So this is a structure. As I mentioned, there are 56 ligands in there, and it's really a wide range. So there's nickel ions, there's this iron sulfur cluster, there's this carbon monoxide dicyano iron, a magnesium. So all sorts of small ions, etc. And then down at the bottom, we also have this organic molecule. So really a wide range of things. But then, you know, I've got 56 ligands in there. How do I score this? And this is something that we spent a lot of time talking about, and eventually just decided to settle on taking the average of the LDDT PLI as well as the average RMSD across. Love it if somebody has a better idea on how to do this. This is what we were dealing with though in terms of number of ligands. So remember, this structure has 56 ligands in it, but there were some people who submitted like 5. There were other people, you could see the majority of the people didn't actually submit the full set. So again, we've got different numbers of ligands. How do we go about scoring that? And then finally, this is an example of where the structure was not fully resolved. So this MQ7, which was in this structure, this was the SMILE string that was supplied, but you can see that the end of this alkyl chain is not resolved and is not in the cryo-EM structure. So there was a lot of things that we had to do, a lot of messing around and manipulating and tuning things by hand to score all of these. Now, this comes back to the other question. So remember this, as Xavier told you about, the LDDT PLI ranges between 0 and 1. When I look at these, I usually look at something above about 0.8 as being a pretty good structure. So, by that metric, we've got structures from this particular target that look pretty good. So, if we look at the superposition of the protein structure for a high scoring submission, looks pretty good. If we look over here at this plot, so remember we're looking at LDDT PLI along the x-axis, RMSD along the y-axis. You want things down here in this bottom right corner. And if we look at, we've got a lot down there from that structure, but it's all of the ions and the sulfur clusters. If you look at the MQ7 ligands, they're terrible, right? They're somewhere between 6 and 10 angstroms away. If we take a closer look at that, so what we're looking at here is we've taken the protein out and we're just looking at the superimposed ligands. So in green, we have the reference from the cryo-EM structure. In magenta, we have the submission. So you can see that these iron clusters fit quite well. The ions are really good, but then take a look at these MQ7 ligands. So the MQ7 ligands from the cryo-EM structure are all here in the core of the protein. In the submission, they're way out on the periphery. So I think we need to come up with a better way of completely capturing that. This is just an overview of the submissions that we had, sort of grouped by target category. As I mentioned, I think 0.8 represents a pretty good structure. So you can see that we did less good on the multimeric structures, but most of the homomeric structures look good. The RNA, there were good submissions there. If you just flip that, this is the same chart, and I just sorted it by the LDDT PLI mean over all of the structures. And you can see, I guess, my rough assessment is there were about a third of these that were really great. There were a third that were pretty good, and a third not so good. So, but here's where the rubber hits the road. This is all of the data. So I've put this into a heat map where rows are submissions, columns are targets. And then if there's a 1 in there and it's a red cell, that means that that particular submission was within 10% of the best. Again, a somewhat arbitrary cutoff, but I think it worked pretty well. Here are the groups that performed the best. I'm very happy that all of these groups will be speaking immediately after me. I think there's a couple of other tricky bits and take homes here in this data set. So you'll look and you see blocks of predictions. So you'll see this red block up here, and then you'll see another red block over there on the right. And that's because we're looking at more or less the same structures. This block over here, this H1171, H1172, T1170 are all the same structure. So it's a time-resolved cryo-EM structure where they were tracking ATP hydrolysis. This is actually pretty tricky and was tricky to assess because you've got 6 ATP binding sites. Those ATP binding sites could contain ATP gamma S, ADP, or ADP plus magnesium. So we were relatively lenient here and just did an all against all comparison with the 5 submissions. The other one over here, this block T1158, V1 through V4 is 4 different ligands in the same protein. So there are 2 prostaglandins there. There's prostaglandin E2 and an analog. There's this steroid. And then the protein also has 2 ATP binding sites. So all 3 of the ligands, the 2 prostaglandins and the steroids, bind in the same site. There's really not a lot of difference in protein structure between those. And then the ATPs bind in a separate site. Perhaps not surprisingly, predictions for the ATPs were much better than predictions for the organics. This is just that same data, and I did it as a Z-score. I apologize. I didn't realize that it was impolite to give people negative Z-scores. I won't do it again. But you know, the nice thing is that the ordering there is about the same as the ordering that we got using that top 10% cutoff. So, you know, what have we learned here? I think we got really good predictions for small ions and endogenous ligands that weren't flexible. So things that were small worked out very well. Predictions less good for things that were conformationally flexible. There was actually one really interesting case where you had 3 macrocycles complex to 2 irons, and each of those macrocycles had a different conformation. Nobody did well on that, but it was incredibly challenging. You know, I think we, after spending a tremendous amount of time scoring these things and then staring at structures, I think that the combination of RMSD and LDDT PLI gives us a good assessment metric, but we're looking for other ways to assess these sorts of things. So love suggestions from the community. I still don't like this idea of averaging over multiple ligands, but I don't really have a better way to do it right now. So love some suggestions there. And then I think this was a great start, but you know, should CASP be doing different sorts of ligand prediction challenges? Would it be good to have something like a D3R type challenge where you provide people with crystal structures and small molecules and ask them to dock them? Would it be good? You know, there were comments that people wanted to just have challenges that were ion specific. So I think there's a lot of possibilities here. Anyway, was fun to do. Thanks for the opportunity.
2 questions. Yeah.
Yes, thank you for the great talk. Speaking of the first time, it's fun turning clock back to CASP2 year 1996. It was a ligand protein docking prediction category. It was fun. But the question is, so the ligand binding sites are supposed to be more conserved, A, because they're in the cavity typically, and B, because they're functionally important. So the structure quality prediction for those should be generally significantly higher than the overall structure of the protein. So how's that, in your experience, maybe how is that different from D3R prediction where you actually get the crystal structure in quality?
Yeah, I didn't, to be honest, it's hard to assess because there were only a handful of targets in this that I would consider to be drug-like molecules. But I think for those, actually, they were really good. Several of them were spot on. There was one beta-lactamase, and the predictions were almost perfect, even though if anybody looked at that, there's a mistake in the crystal structure for that molecule. There's an isoxazole with an sp3 carbon. You cannot have an sp3 carbon in an isoxazole.
So on the ligands being so good, the ions being so good, how much could people get from homology with other structures for this set in general?
Yeah, I haven't really looked closely at that. I wanted to actually go back now that AlphaFill is out. I wanted to take some of the structures here and run those with AlphaFill because I think it would be a great way to position a lot of these natural substrates and ions. So haven't had the chance to do it yet, but it's something that I definitely want to do.
Okay, so I have two related questions. Were any of these covalent complexes?
No.
Okay, and then a related question is there any interest in or potential to look at relative binding affinities or things like that?
Oh, I'd love to do that. I mean, that's what we did in D3R. So yeah.
Because you need the data, but
Yeah. Yeah, and then which data do you want? Yeah.
Did you see any difference in terms of between cryo-EM and crystal structures in terms of interest, like novelty of binding sites or how hard they were?
Yeah,
predictors?
The cryo-EM structures were much harder. And I think, it's just because they were massive and they had lots and lots of ligands associated with them.
Okay, I don't see any more questions. Then let's thank Pat again.